Okay, so moving on, we're going to talk now about another technique in kinetics. The technique is called the integrated rate law technique. It's sometimes discussed under the heading reaction concentration and time. And again, you see here I've borrowed some slides from the Masterson and Hurley textbook. Basically, if we look at our rate equation, so we've got, something like rate is equal to Ka, and you remember what this is presuming is a reaction. We've got A going to products, right? So the actual value of the rate, you remember we talked about looking at time versus, say, the concentration of A, and what we'd see is that A goes down over time, and it's kind of a curving curve like that. So we defined rate as negative delta A delta T, and leaving out any issue of any coefficients or anything there with that. If you translate those deltas into calculus language, that's negative dA dt, that's a differential expression. And this is in fact a differential equation, and we could solve this if you go on to differential equations, you could see that this is dA over concentration of A is equal to negative K dt, and that if you integrate both sides from time equals 0 to time equals t, I guess this one should be the 0 to t, and then this is from A at time 0 to A at time t, what we get is the natural log of the concentration of A going from time t to 0 is equal to negative kt, because negative k0 is 0. Anyway, this is a differential equation. We might see this as ln A at time t minus ln A at time 0 is equal to negative kt, something like that. Anyway, this technique, all this stuff here is not something you're going to do in general chemistry so much, but it's kind of nice if you've got the calculus to appreciate that comes from that. So these things that we get are called integrated rate equations, because that's what we did back here. This step right here is the calculus technique of integration. So, here's some images of a reaction that's going on, and over time, how the reaction happens, and if you increase the concentration, that affects the rate. Is faster. So this is the first order integrated rate equation, and you may recognize this is the same thing I just wrote for you a minute ago. In one of the rules of logs is that the natural log of x over y is equal to the natural log of x minus the natural log of y. That is what we just saw. K is the rate constant, and T is the time in the same units that the rate constant's time units are in. If we do that separation, if we express ln A over A naught, where A naught is the initial concentration, and we can plot these data on a XY graph where T is the X value and ln of A is the Y value. And if we measure the temperature, measure the concentration of A at several different times, what we're going to get is a series of data points that form a straight line with a negative slope. And so the data points might look like that, and we might draw the best straight line we can through that. The slope of that straight line is going to be negative k. The y-intercept of that straight line is going to be the natural log of the initial concentration. That's a graphical interpretation of that. So here are some data. We've got a dinitrogen pentoxide. It's being decomposed, and at 67 degrees Celsius, something called the half-life of that is 2.0 minutes. And so what you see here is every 2 minutes the concentration halves, And that, again, one of the things that that a lot of folks don't understand, and by a lot of folks, I mean if you went through the U.S. Senate, for example, and you asked them to define half-life or asked them how much was left after 2 half-lives, I'm convinced that 75 of them would not be able to answer the question correctly. That what happens after 2 half-lives is not that it's all gone, it's that we have 1/4 left. It's half of the half that was available after the first half-life. So anyway, but so taking this example, we can figure out what the initial concentration was, for example, or the concentration at any given time. If you know the initial concentration here, so you're basically being able to ask, what's the concentration after 6 minutes? If you started at 0.2, so you plug in 0.2 here, you plug in your 6 minutes here, you're given that the rate constant is 0.35 minutes, which is that right there. These guys are in the same unit, so they cancel out. And we find out that that ratio is equal to, this is 2.1. We've got this log over here we got to get rid of. So what we do is we take e to both sides, right? So e to the log is just this, that value there, that just gets rid of the log. E to the 2.1 is 8.2, so that lets us calculate what the concentration is. Of course, it's always kind of comforting if you know the initial is 0.2, you know something at a later time. It's got to be less than that. If that goes up, something's wrong, right? So watch out for that kind of issue. Now, the second question here was, how long will it take it to get to 0.15? So what we do is we take, let's see, what are they doing? Are they just using half-life for that? If we start at 0.2 and we're trying to get to 0.15, here we have, right, so okay, what they've done is they've taken that relationship, ln A naught over A is equal to KT, right? That's that first order relationship they expressed up here, right? That relationship there. And they've solved it for t. So all they've done is divided this side by t and multiplied this side. I'm sorry, divided that side by k and divided this side by k. So that's where this 1 over k ln A naught over A comes from. This is the value of k we were given. That's the initial value. That's the value we're asked to figure out how long we're getting to, the 0.15. And that gets us to the time for that one. And then we're asked to get the half-life, or the time for a half-life there for half a sample. And what we do there is say whatever the initial value was, then the initial, the value at the half is going to be the initial value divided by 2. So that means that the initial value is just equal to 2 times that value. So if you have the value, to, N2O5 naught over N2O5 at time t, so the top one's time 0, the bottom one's time t, we've decided that if we're going to half, then this is going to be 2 times N2O5 at t1 half, and this will call us the N2O5 at the T1 half. Whatever that value is, the concentration at T1 half, they cancel out. So that's just 2. That's where that 2 comes from. So if we take this back to the equation that we derived that looks like this, put that around there, we've now got ln2 here because that's the value of those. And ln of 2 is 0.693. So whatever our value of k is gets divided into 0.693, and that gets us our half-life, or t sub 1/2 is our half-life, and that's going to be in minutes. So you can get, or it's going to be in time units, whatever the k value time units are in. So you can get from t1 half back to the rate constant, R from the rate constant T1/2. And again, this is for first order, right? This is all for first order reactions. Now, here's that actual definition here of the half-life expression. And in first orders, that's independent of the starting concentration. So one example of first order decay is radioactive decay. And again, I mentioned that senators probably don't understand this. You know, one of the issues we have to deal with nationally is what to do with all the radioactive waste that we have, and how long do we have to store it until it's safe. And the bad news is 2 half-lives isn't enough. Right? So here is a radioactive isotope, plutonium-240, and we're told that after 1,000 years, 10% of the sample decays. So we're asked initially to calculate the half-life, and we're asked to determine how long does it take it to take a 2-gram sample to 15% of the original amount, and what is the rate of decay of a 5-gram sample in grams per year. So what we're going to do to get the half-life is we're going to take this data, right, that 10% decay. So what this right here tells us is that time amount 4.60 grams is how much we have at 0 times 0 at time 1,000 years. So these are in years. 10% of that has decayed, so that means 10% of 4.6 is 0.46. So this is going to be 4.6 minus 0.46. That's going to be 4.16 grams. So we've got 2 data points there of how much we have. And we're going to express, concentration is going to be expressed in grams. We're okay with that. So again, that's just what they're doing here. That 4.14 is what I figured out up there, and so we put that into our equation. And again, this is going to be the 4.6 is x naught, 4.14 is x, t is 1,000 years, and if you work that out, you get that the rate constant is 1.05 times 10 to the negative 4th per year. And then if you divide that into 0.693 or ln2, we get that the half-life is 6,600 years. Taking that on, we want to know how long it's going to take to get 15% done. So now we're going to take our rate equation again. But now we don't know what time is, right? We do know what the K is that we calculated above. We figure that out in A above. Now we want to get 15% of it. So if the initial mass is 2, 15% of that is going to be 0.15 times that. That's going to be something like 0.30, right? And if you work this out, you find that T is 1.8 times 10 to the 4th year. So let's see, that's 18,000 years. Right, so get back to me when that's done, right? That's about how long it takes me to grade things, too, I think. All right, then the last question. What was the last question? The last question was what is the rate of decay of a 5-gram sample in grams per year? So if we go down here and look at that, the rate is first order, right? We know that the rate is K plutonium-240. Okay, and that this is a 1, right? So all we do is take the K value that we got from part A. So again, we calculated that in part A, and we take the 5 grams we're given, and we find out that at the initial time, at least, it's decomposing at the rate of 5.25 times 10 to the negative 4 grams per year. So that's 525. So 1, 2, 3, 4, so that many grams per year. So watch it real close if you want to see it react. It's not gonna have to watch it very carefully for a long time. All right, going into second order reactions, the equation's a little bit more complicated, and you may think, wow, well, at least it doesn't have logs in it. That's true. But what we wind up are with these reciprocal equations, and so that our 1 over our concentration at time t minus 1 over our concentration at time 0, the initial concentration, is going to be equal to the product of kT. So graphically, what we do is we plot 1 over A on our y-axis, T on our x-axis. We're going to get a line now that goes up. So here are some possible data points, and we draw the best straight line through that. The slope of that line is positive k now, not negative k. And the intercept here is 1 over the initial concentration. So that's the graphical interpretation of that. The half-life, interestingly, comes out to be dependent on the initial amount. So the half-life is not constant. It's not a consistent value throughout. And again, what you do to get that is you'd say 1 over a to the t time t minus 1 over 2a to the t. We're saying that a to the t is half of a0. That's equal to k t1 half. If you solve that equation, you wind up with that expression for half-lives. A zeroth order reaction, you've got some cases where the concentration doesn't matter, and that gives us the case where we have a linear plot of concentration versus time. And what happens then is that the rate, the line again goes down like so. The y-intercept is the initial concentration, and the slope is negative rate constant of a zero order plot. And this one also does not, the half-life does not depend on that initial concentration. So if we look at the case of the composition of hydrogen iodide on a solid surface, this is a zero order reaction. So what's happening here is we've got gold metal, and HI is being pumped over the gold metal at a high enough temperature where this reaction happens, and each HI produces a half mole, or each mole of HI produces a half mole of H2 and a half mole of I2, all in the gas phase. And I thought we were going to look at we got an example after that. This table is kind of a useful one. I like this table a lot because it does have the orders, the rate expressions, the concentration time relationship, the half-life equation, and the linear plot all there for you. So here's our example of the hydrogen iodide case. So we have to figure out whether it's zero first or second order in HI. So what we would do is we would make plots of each one of these and see which one fits best. Those plots, should be if it's just HI itself, then the plot of this on the y-axis and that on the x-axis should be linear. So that would be the zeroth order. If we think it's first order, if it was first order, then if this is x and that is y, that'd be the first order plot. Okay, so that column and this column. And then finally, if I plot x as time and I plot 1 over HI as that would be my second order plot. So what you'd have to do is plot those data points. And of course, what we did here is we took the natural log of that to get that number, and here we took 1 over the initial value to get those numbers, that's easy to do in a spreadsheet. And so if you look at the plots, what you see is that the straight line plot in this case looks like the 1 over HI is that. So they say here that this is second order according to these data, even though they said it's a zeroth order reaction before. This one looks like a second order because this is a good straight line. This is not straight. And this one's not straight. They're all both curved lines. Now, the sad truth is, in real life, it's not always that clear. So I have tacked on down here, there's an Excel file, and I'm going to open that up and see if I can get that for you. It'll give you a little warning, but it's okay. You can open it. And let me drag this back over here, and hopefully we'll be able to see this Excel file. So what I did was I looked at a problem in your in OpenStax, and actually this is from the other version of OpenStax, but this is a problem where we're given SO2Cl2, which I believe is thionyl chloride. We're given concentration time data for that. That's what's highlighted in yellow there. And what I did was just right over here in this box, if you look up here at the top, right up here, you can see that I said LNA4, which is the cell here. A4 is the cell number. So this column is taking the natural log of whatever's in the first column. That's my first order check. My second order check is taking 1 over that. So if you see, it's 1 over whatever is in A4, 1 over whatever is in A5 if you're looking up here in the entry line. So I gathered my data, and then what I did was I used the insert tab and inserted a scatter plot, which is this one right here. And my first order scatter plot is over here. This is what this looked like. Now, I've spent some time learning how to make a good scatter plot, and I've got the graph set up so that it's nicely, it's occupying most of the graph. I've got the values for the axes and things like that all set up. And I have over here on the graph the calculated equation that Excel has calculated for it, and this value of R squared. And what R squared tells you is how well the data points, which are actually the little blue points there, how well they agree with the straight line, the linear regression line, and 1 is perfect agreement. So the first order fit has perfect agreement. If I look at the second order fit here, let me see if I can get that. Here's my second order plot, and you see that the R squared is 0.9847. Now that's a really good fit, but it's not as good as perfect. So so my conclusion from this is that this is a first order reaction. And I wrote that up here. So looking at graphs, this is first order. The slope of that gave me that value, which then gives me this rate, and the units are seconds to the -1 there. So that Excel chart is an example of how I would work that kind of problem. And so you can open that up from the OneNote page and maybe learn by dissecting that Excel chart how to do these sorts of problems. I have fun doing those. I feel like I'm doing real science when I'm doing that. And like I said, I have the benefit of having done kinetics professionally for a while, and I can tell you that that one is more realistic than the one that we saw above, where it was really, really, really clear that it had to be second order. The HI case here, it's usually not that obvious. All right, hope that helps.